Okay. Thank you, Arina. So welcome to the presentation, everyone. So before we start off, this is going to be not too long. So I'm hoping about 35 minutes. If we are too slow, then maybe 40 minutes, but not more than that. Um, so maybe we can start. So I'm going to be talking about the number of edges in maximal 2-planar graphs. Um, and this was joint work with Michael Hoffmann. Uh, okay, now it works. Okay, so so what are planar graphs? Planar graphs are graphs that can be drawn on the plane such that the drawing has no crossings. So for example, K4 or the complete graph on 4 vertices is planar because you can draw it this way. A very well-known result, one of the classical results, is that every planar graph has at most 3n minus 6 edges. This is known. So now we also have the concept of maximal planar graphs. So what are maximal planar graphs? Maximal planar graphs are graphs where you cannot add any more edges such that the graph still remains planar. Let's say let's try to understand this in more detail. Let's say we pick some graph. So for now, this is just a drawing. So the graph can have other drawings as well, but let's say we pick this drawing and let's try to keep adding edges to it let's keep adding edges to this graph such that it still remains planar. So this has 7 vertices. We can add some more edges. We add more edges. And in this particular drawing, we see that we cannot add more edges. So addition of any edge kind of creates a crossing. So for this drawing, we cannot add more edges. We cannot add any more edges. Another thing that is known, it's known is that every maximal planar graph has exactly 3n minus 6 edges. So you can kind of observe here that every planar graph has at most 3n minus 6 edges. But if we try to obtain maximal planar graphs, that is, we keep adding edges to this graph until it remains planar, then we always end up with a graph which has 3n minus 6 edges. So now let's go back to this drawing on the right, and let's count the number of edges. It turns out that this has 15 edges, and which is exactly 3n minus 6. So this shows that this drawing was maximal, obviously, because this is how we drew it, but also the underlying graph or the graph induced by this drawing is also maximal planar. So what we observe now here is that maximal planar graphs or the set of maximal planar graphs is the same as the set of maximum planar graphs, where we can interpret maximum planar graphs as graphs that have exactly 3n minus 6 edges. And sometimes these are also known as optimal planar graphs or planar graphs which achieve the maximum edge density. Okay, so now we've understood stuff about planar graphs. Let's now look into 1-planar and 2-planar graphs. So what are 1-planar and 2-planar graphs? Let's look at the more generic definition of k-planar graphs. So a graph is called k-planar if it has a drawing where each edge has at most k crossings. So for example, k5 is 1-planar because we can draw it in the plane such that there's at most 1 crossing per edge. Similarly, K7 is 2-planar. Again, we know the maximum edge densities of these graphs. So we know that any one planar graph has at most 4n minus 8 edges, and any 2-planar graph has at most 5n minus 10 edges. Now again, we have the concept of optimal 1-planar and 2-planar graphs, and these are graphs which have the maximum density possible. So these are graphs which have exactly 4n minus 8 or 5n minus 10 edges. So these graphs achieve the maximum density possible. Now, what about maximal 1-planar and maximal 2-planar graphs? What happens to these edge densities? Is it going to be similar to 1-planar graphs where we figured out that, or we saw that any maximal planar graph has the same number of edges or as the highest possible, or what happens here? It turns out it's not true for one planar and two planar graphs, because we have examples of graphs, or we have examples of a maximal one planar graph which has only 2.64 n edges, and also we have examples of maximal two planar graphs which have 2.63 n edges, and we can kind of see that these numbers are not close to 5n and 4n. So let's look at this in more detail. So what happens with one planar graphs? So in 2012, Brandenburg et al. Studied maximal one planar graphs and constructed a graph class which has 2.64 times n edges, and this is and these graphs are maximal one planar. Essentially, what they did, just to understand, is that they took this graph here on the left, made multiple copies of it, such that so they made multiple copies of it and attached them at this common A and B vertices. And they were able to show that this graph has 2.64 n edges. And in addition, they proved that every maximal one planar graph has at least 2.15 n edges. So they also gave kind of a lower bound, saying any maximal one planar graph has at least 2.15 n edges. And this lower bound was later improved to 2.22 n. Now, kind of something similar, but not as extensive as happened with two planar graphs. There are examples of two planar graphs or maximal two planar graphs with 2.63 n edges, and we did not know any lower bound until now. And to kind of understand how this graph looks, maybe you can recall this Buckminster fullerene. This is the carbon atom or something, which kind of looks like this with alternating phases of size 5 and 6. So basically, they took this molecule, and for every phase of size 5 and size 6, they added some edges inside. So for a phase of size 5, they added all the edges inside, and for size 6, they added 3 diagonals. And then what they did was, for each of the edges of this molecule, or like the one of the uncrossed edges, they added vertices of degree 2. And we call these vertices of degree 2 as hermits, which we will look into more detail later. But just to kind of understand or see in more detail how this graph looks like is basically this. We have these size 5, size 6, 3 diagonals here, and all the edges here. And for every edge, every uncrossed edge, we have these hermits. Okay, so now what do we know? This is what we know now. For one planar graphs and maximal one planar graphs, we know that any maximal one planar graph will have at least 2.22 n edges, and at most 4n minus 8 edges. And for what we wanted to study was with maximal two planar graphs. And the exact question we wanted to study was, how sparse can maximal two planar graphs be? And this is our result. We were able to prove that every maximal two planar graph has at least 2n edges. And then we were actually able to prove that this bound is tight, because we were able to find a graph or a set of graphs which have 2n plus some constant number of edges, and all these graphs are maximal two planar. So essentially, we were able to change this or improve these bounds, give a lower bound of 2n, and prove that it is tight. Okay, so now it's clear about what we tried to do is clear. Now, how did we do it? And let's go into the details. In general, how do you prove a lower bound on the edge density of some graph class? There are multiple methods. Maybe you can look at charging schemes, and many other things have been done in literature. What we do is the following. I'll first quickly give an overview of what we do, and then we can go into details of each step. But yeah, so what we want to do is look at a maximal two-planar graph. So let's say we pick some maximal two-planar graph, some arbitrary graph. Then the next thing we do is we pick a drawing of this graph. And then we analyze this drawing that we picked. And what exactly do we analyze? We analyze the number of low degree vertices. And what do I mean by low degree vertices? I mean vertices of degree 2 or degree 3. And then we also look at the neighbors of these low degree vertices and possibly even their degree. So these red vertices are like the low degree vertices. Then we look at the neighborhood of these low degree vertices. So look at these neighbors, their degrees. How does this neighborhood look like? So we analyze these from the drawing. Then we count the number of edges that support this low degree vertex. Now, what do I mean by support this low degree vertex? Let's say we have this degree 2 vertex. All the edges kind of around it immediately have to be present in the drawing to somehow block edges from being added from this vertex to some other vertex in the graph. So these crossed edges are somehow mandatory to be present around this vertex and kind of support this vertex. And once we have all these properties from the graph or from the drawing, then we can now count the number of vertices and edges and obtain a lower bound. So we follow this approach. The first step is to pick a drawing. Now the question is, what drawing do we pick? We will get to that. The second step is to analyze this drawing, find properties, and get as many details as possible. The third step is to finally count the number of vertices and edges. Now let's go through each of these steps in more detail. The first step was to pick a drawing. Now, what kind of drawing do we pick? Ideally, we would want to pick a drawing which will help us in analyzing the drawing better. So we want to pick a drawing which makes our life easier and has multiple properties. So we pick a drawing with the least number of crossings. Okay, makes sense because it's easy to argue about crossings, or we can find easy contradictions with the number of crossings. But in addition, picking the drawing with the least number of crossings has another advantage. That is because we know this theorem that for a two-plane drawing or a two-plane drawing that minimizes the number of crossings is also a simple drawing. So before that, let's understand what a simple topological drawing is. So a simple topological drawing, or sometimes even called as just a simple drawing, is a drawing where any two edges have at most one point in common. And this is including common endpoints. So two independent edges are not allowed to cross more than once. And two adjacent edges are not allowed to cross because they already have one point in common, which is their common endpoint. So what is allowed is something like this, where independent edges cross once or don't cross each other at all, or if adjacent edges don't cross. So now let's bring back this theorem and let's try to understand. What this theorem states is that if you pick a drawing, or if you pick a two-plane drawing that minimizes the number of crossings, then it is also going to be simple. So by picking a drawing with the least number of crossings, we get two properties. It has the least number of crossings, and secondly, it is going to be simple. So we can use these properties while we analyze the drawing. So this is the drawing we pick. And in addition, we have this following property that every maximal two-planar graph is two connected, which means that you do not have any vertices of degree 1 in any maximal two-planar graph. So the minimum degree is 2. So when we are trying to analyze the drawing, we only have to start with vertices of degree 2 and degree 3 and try to look at these low degree vertices is what we care about. Let's go to the second step, which is where we kind of look at the drawing itself, the low degree vertices, and how does this drawing look like. So before that, what are we trying to do? we are trying to analyze the drawing and look at the low degree vertices. Now, why do we look at these low degree vertices? So if you're able to look at the low degree vertices, look at its neighborhood, and if we are able to say something like for every low degree vertex, there need to be X number of high degree vertices in its neighborhood, then in our overall counting of number of edges, we can always say that for every low degree vertex, we have a lot of or X number of high degree vertices. So the total number of edges increases. So this is why we want to look at low degree vertices and get a handle on how they behave in our drawing. Okay, so let's look at the step 2. We look at low degree vertices. We start with degree 2 vertices, which we call hermits. Let's say this is, so this is our degree 2 vertex. The first question, so let's say we look at this vertex in our crossing minimal 2-plane drawing. The first question we ask is, can these edges be crossed? Maybe they can be, maybe they may not be, but let's try to analyze this. Recall that we have a 2-plane drawing. So this blue edge can have at most 2 crossings. So it can have one more crossing either on this side or this side. And let's say it's on the other side. So here what you can immediately see is that we can maybe add an edge between this vertex to our degree 2 vertex. But we may not be able to do that if this vertex is same as one of these 2 vertices. So the red vertex is already incident to these vertices. So let's see if that is possible. Can this vertex be the same as one of these 2 vertices? In the first case, if the vertex was the same as the left vertex, now we see that we have this black edge and this blue edge crossing each other, but they're also adjacent. Now you can see that because we said that our drawing is going to be a simple drawing, this is not possible because we have 2 adjacent edges crossing each other, which is not possible in a simple drawing. So that is not possible. The first case that this end vertex of this blue edge being the same as the left end point is not possible. Maybe it can be the same as the right vertex. Okay, so then now let's consider cases. The other edge of this, the second edge incident to the hermit may have crossings. Let's say if it does have crossings. In this case, what we can do is take this black edge and reroute it along here. And now what we obtained is the same graph, or okay, I'm sorry. So now what we obtained is a drawing of the same graph. It's still 2-plane because we did not introduce any crossings. But what we did is get rid of this crossing. But this is again a contradiction because we started with a crossing minimal 2-plane drawing. So we should not be able to move edges around and decrease the crossings further, which basically means that the second edge has no crossings. But now again, it's easy to see that we can now reroute this blue edge itself to kind of go around here and eliminate this crossing, which is again a contradiction because we started with a crossing minimal drawing. This basically gives us that if you look at any hermit or a degree 2 vertex, both its incident edges must be uncrossed. So that's the first property we obtain for these degree 2 vertices. The next property we immediately obtain is that the neighbors are incident to each other. Because these 2 edges are uncrossed, we can immediately add an edge between the 2 neighbors and ensure that this edge is uncrossed. So it should already be existing. Okay, so now let's look at this face here. We have this degree 2 vertex here, and we know that it's exactly degree 2. So it should not be possible to add an edge from this red vertex to any other vertex in the graph, which basically means that we should along this phase or in the phase here, there should be no other vertex except these already 2 existing vertices. So in some sense, the space should be bounded by a sequence of doubly crossed edges, maybe two edges like this or more than two, but it should always be bounded by a sequence of these doubly crossed edges such that there is no other vertex on this boundary. Now, symmetrically, we can basically move the hermit to the other side of this edge, and we need the face to be closed off in a similar fashion. So again, we should have these crossed edges bounding it. Now, what we immediately see is that the degrees of the neighbors is at least 4, because we already had these two edges here, and we have two more edges which help bounding or closing this vertex off. So the degree of both the neighbors is at least 4. Now, another property we can obtain is that the degree of at least one neighbor is at least 5. I would not go into the details of this, but it's kind of similar. You assume that the degrees of both the neighbors is exactly 4, then you can say that, oh, if otherwise I can add more edges and obtain an easy contradiction. And it gives us that at least one of the neighbors should have a degree 5 or more. Okay. The next thing is to look at the to look at the neighborhood and look at the edges and how they support this hermit. So firstly, this edge here, kind of which is, the edge that is incident to both neighbors of the hermit, we say that this edge hosts the hermit because somehow this edge is private to this hermit, and there cannot be another hermit that is also hosted by the same edge. So in some sense, this edge, the edge highlighted in green, is private to the hermit, including the two edges incident to the hermit. So all these three edges are kind of private to this hermit. Let's look at the two edges that appear in immediately before and after in the rotation system of the neighbor. So as I kind of mentioned before, these edges are required to help block this hermit from the rest of the drawing. So in some sense, these are hosting, or these are supporting the hermit. So we would like to count the number of such edges which support the hermit, or in other words, we can kind of say that the hermit here. Okay, where's my mouse? Yeah. So in some sense, we want to say that the hermit here claims a bunch of edges. So it already claims these two incident edges and also the base, or like the edge that hosts the hermit. Now we want to kind of count how many other edges can it privately claim. So now we are looking at these two edges. But it turns out it can happen that this blue edge here supports two hermits. And this hermit kind of has more, and let's try to add more things to this. And it turns out something like this can happen, where at this vertex, we have multiple incident degree 2 vertices. And each of these boundary edges, this cross boundary edge supports two hermits. But what we can still do is go counterclockwise and say that, or assign this boundary edge to this hermit and do the same around. So, and then we take the next boundary edge, assign it to the next hermit, and so on. And by doing this, we get that each hermit has 3 private edges at each neighbor. And how do we obtain 3? So we have one boundary edge and one edge that is incident to the hermit, and also the base of the hermit. Okay, so now this kind of finishes the so this kind of finishes the hermits, or how the hermits look. We know how hermits are, we know the degrees of its neighbors, and we know how many private edges each hermit has. Now we also have to look at the other low degree vertices, which are basically degree 3 vertices. So let me quickly give you an overview of how these would look. We would not go into the details. How will these degree 3 vertices look? So we have this red vertex, which is a degree 3 vertex, and 3 incident edges. Maybe we have all three of them uncrossed. We could also have one crossed and two uncrossed. Or we can have that in the drawing, two of them are crossed and only one of them is uncrossed. We also have the third type where all of them are crossed, but it turns out that this can actually not happen in the drawing. So let's ignore that. So we have three types of degree 3 vertices that can occur in our drawing of, in our maximal 2-plane drawing with minimum number of crossings. Then we also have degree 4 vertices. Now, so in some sense, we do not care about degree 4 vertices unless they are adjacent to a degree 2 vertex. Now, this is because if we have a degree 4 vertex, so since we're trying to obtain a bound of 2n, in some having a vertex of degree 4 is fine. But then if we have a degree 2 vertex adjacent to this degree 4 vertex, then we can, by increasing these type of degree 4 vertices, we also increase the number of degree 2 vertices, which brings the edge density down. So we also want to understand how these vertices look like and how these neighborhoods look like. Maybe I can, okay, let's say I can quickly give you some details of this type of degree 3 vertex. So we have this degree 3 vertex with one uncrossed edge. And again, we look at these edges and see where the endpoint is. Like, the analysis is very similar to degree 2 vertex, because let's say we have one endpoint of this, we can add an edge between the degree 3 vertex and the endpoint of this vertex. That should not be possible. So it should already be adjacent to one of the neighbors. And with some extra analysis, we can show this does not happen. And this is the only way it can look like. So the first thing we see is that this neighbor of this degree 3 vertex has a degree of 3. And we can show that, or we can redraw some more things and then some with more. So we can basically look at the drawing and see how things work and analyze the drawing, and then finally show that the degree of this neighbor is actually 5. So for every degree 3 vertex, there should be a vertex of degree 5 in its immediate neighborhood. Then we can also show that this edge is obviously private to this degree 3 vertex. And it turns out that we can also claim these two edges. So every degree 3 vertex has 3 private edges, or it can claim 3 edges at its neighbor. I mean, it needs some more additional proof. Why can this not be claimed by something else? But let me skip that. We can come back to that if there are some questions. Okay. So now I gave you an overview of how we analyze degree 2 and degree 3 vertices, or one of the degree 3 vertices. Then we kind of do the same with the other two types of degree 3 vertices and the degree 4 vertex. And with all these properties that we obtain, let's now go on to step 3, where we count the number of edges and vertices in the drawing. So, okay, so let n be the number of vertices, let m be the number of edges, and we denote by vi the number of vertices of degree I in this graph. The first two equations is quite simple. The total number of vertices is basically the sum of vertices of different degrees. And this is basically, the second equation is basically the handshaking lemma, where we count, which is basically twice the number of edges is the sum of the degrees in the graph. What next? We obtain one equation from the Hermits. So recall we went through the Hermit, found some properties, and what we basically showed is that for each Hermit, or for whenever we have a degree 2 vertex, it must have 2 neighbors of degree 4. So yeah, so it must have two neighbors of degree 4, and further, it claims 3 edges at each of its neighbors. So we kind of put it in the form of an equation and say that, and we kind of double count the number of edges and say that 2v2 is lower bounded by, or is less than equal to the summation, where we start the summation from I equal to 4, because for every degree 2 vertex, there should be 2 degree 4 vertices. And then we kind of do the same with degree 3 vertices as well, because we said, again, we said that for every degree 3 vertex, there should be a vertex of degree 5 in its neighborhood. So that's why we start the summation here at 5, and it claims 3 edges. Okay, so then we add these 2 equations, but obviously I skipped many details while I was explaining these things. What these 2 equations in reality look like this. It might look quite complex, but then let me quickly explain what these H1, H2 mean, and then it becomes quite clear. So V7, H2, or basically this H2, or the number beside H, represents the number of degree 2 vertices that the vertex is incident to. So if we look at a V9, so V9, if there was no superscript, V9 meant the number of vertices of degree 9. With the superscript H2, it basically means the number of vertices of degree 9 that are adjacent to exactly 2 hermits. And now why do we do this? Because it just makes our life easier in terms of the calculations. We can, for example, we can say something like, if there is a degree 9 vertex which is already adjacent to 3 hermits, then it cannot have too many degree 3 vertices. It just makes it easier to split and analyze the high degree vertices in terms of the number of degree 2 vertices that they are adjacent to. Okay, and one more thing I would like to point out here is this V4H1. This is exactly the degree 4 vertex that I showed you in one of the previous slides, where you have a degree 4 vertex and an adjacent hermit. Okay, so now we obtain these 2 equations. Now, finally, what we do is calculate the value of m minus 2n. So we have these equations. So basically substitute these 2 equations and these 4 equations into m minus 2n. I skipped the math, but essentially what we get is that this is greater than 0, which immediately proves that the number of edges in this graph is at least twice the number of vertices. And this ends the proof. Okay. How much? Okay, more. I'm at 33 minutes. Okay, so now what we did was basically prove the lower bound. I went through, just to quickly summarize, we went through all 3 steps. Or we picked, or we analyzed what kind of drawing we can pick. And then we saw how to look at the low degree vertices and the neighborhoods and the edges and how to claim these edges and stuff. And then we finally put all of it together into these equations and showed that using these equations, when we compute the value of m minus 2n, it turns out that it's at least 0, which immediately gives us that the number of edges is at least twice the number of vertices. Okay, so now let's quickly go to the upper bound. So recall that I claimed we have graphs which have 2n plus some constant number of edges. Now, how did we construct these graphs? We start with 10 cycles, or cycles on 10 vertices, and we can basically extend the number of layers this way with as many layers as we want. But let me show you an example with just 3 layers. So we have 3 layers, or any number of layers of 10 cycles. Then what we do in the next step is add a matching, or like a twisted matching. So for every 2 consecutive layers, we add these edges to kind of connect the 2 layers, but we add the edges in somewhat a twisted fashion. and end up with a graph like this. This is basically matching between the vertices of the inner layer and the immediate next layer, but we kind of twist them around and add these edges. This is the base of the graph. What we do next is we have this gadget. This gadget is basically a graph on 9 vertices minus K2 plus K2 plus P3. Maybe I can show you which edges are missing. So we take a K9, and these red edges are the edges that are actually removed from this K9. Okay, so we start with the K9 and remove these edges to obtain this graph. Yeah, so then we pick this gadget, we take this gadget and attach this gadget to every edge of the innermost cycle and the outermost cycle. Not to the ones in between, but just the innermost and the outermost cycles. So for every edge here, for every green edge in the inner cycle, we add this gadget such that we basically coincide these two vertices with the two vertices of the edge here. And this this is the construction of our graph. Now what we want to prove is that this is 2-planar and it is maximal. To prove that it is 2-planar is easy because we just have to give one drawing, which is 2-plane, and that is the drawing that is shown on the slide right now. This drawing has at most 2 crossings. Every edge has at most 2 crossings per edge. So this is 2-planar. Now what is more important or what is more difficult is to prove that this is indeed maximal. How do you prove that a graph is maximal? The only thing a brute force approach would be to say that so you take the graph and you add an edge to this graph, and then you prove that the graph that you obtain is not 2-planar anymore. And then you'll have to do this for every edge possible. That is one method. The other method to show that a graph is maximal is maybe you can show that this is the unique 2-plane drawing of the graph. So if this is the only possible 2-plane drawing of the graph, then you can just directly look at the drawing and see if you can add any edge to this drawing. And that makes our life easy because we only have to look at this drawing as opposed to like not knowing how many drawings the graph has. And in that case, you have to add an edge and exhaustively search through all possible drawings of the graph. And we follow the easy approach, or I don't know how easy it was, but basically we follow the approach where we tried to show that this drawing is actually unique. We wrote a computer program which basically told us that this drawing is unique, which solves most of our problem. And the last step is to basically add these edges in the inner cycle and the outer cycle along with this gadget. And then now it's easy to kind of observe that every vertex has a degree 4, except the ones on the inner cycle and the outer cycle. But those are a constant number of edges that are added to this graph. So in summary, we basically obtain a graph with 2n plus some constant number of edges. So to summarize, we basically have this. We have lower bounds and upper bounds. So for 1-planar graphs, for maximal 1-planar graphs, we knew a lower bound of 2.2n and an upper bound of 2.63n because we had constructions of graphs with exactly these number of edges. What we proved is the third row in this table, which is basically saying that for maximal 2-planar graphs, the lower bound and upper bound on the edge densities is 2n. What I would like to end with is for you to observe what is happening here. As we go down, so in some sense, as we go down this table, the edge density decreases. But it's kind of counterintuitive because as we go down the table, we say that we go from planar to 1-planar to 2-planar. So we allow more number of crossings. So in some sense, it gives us more freedom, but we instead end up getting graphs with fewer number of edges. So yeah, I would just like to point this out because it's counterintuitive, but it somehow works like that. And to end, so the first obvious question is, can we improve the bounds on edge density of maximal 1-planar graphs? Because it's kind of, it's 2.2n and 2.6n. Can we use the same approach that we did for 2-planar graphs and improve these bounds? This is something that we're currently working on. And obviously, we can also ask about 3-planar graphs. Why? I mean, it's not too easy to be increasing the number of crossings and still analyze these sparse maximal graphs. But I feel like for 3-planar graphs, it's still doable because we also have this additional property that crossing minimal drawing of a 3-plane graph is also simple. So we can utilize this property and maybe we can do the same and obtain some bounds for 3-planar graphs. Thank you. We can take some questions now.
Yeah, thank you for your nice talk.
Thank you.
Are there any questions in the audience?
I have a small one.
Mm-hmm.
We might have discussed this before. I'm not sure. Sorry, but the upper bound goes down as your freedom goes up, right?
Yes. Yes.
At least for 0, 1, and 2-planar.
Yeah.
Is it clear that it continues this way, or could that just be some kind of weird small number coincidence?
I am not sure. I mean, in some sense, I understand. Okay, maybe like I can draw. Okay, where's my pen? So I try to analyze this and try to understand why this happens. And what I was able to come up with, or like to kind of convince myself. So when we look at planar graphs, maybe I can draw multiple edges here. I don't know, obtain a triangulation.
Mhm.
Now, when I say I have a 1-planar graph, what I can do is basically add something like, I don't know, add one. I can instead of adding all the red edges, I can just add these 2 blue edges, which stops me from adding all the other edges I could have. But by adding these 2 blue edges, I am now limited to add edges within this region. So now I can add edges only within this region. I cannot go from this region to the other region, which I could have done in planar graphs. And again, like if let me change the color. If I'm now allowed to add 2 crossings in a 2-planar graph, I can do the same, add 1 more crossing and decrease the number of, decrease the size of my regions. So somehow I feel like this is what makes the edge density go down. But
there is no proof that kind of
No.
shows that this behavior has to continue.
No,
Okay.
no, I'm not even sure about 3-planar graphs.
Okay.
I haven't looked at it.
Thanks.
Any other questions? Okay, seems like it's not the case. So thank you again.
Thank you so much.
Yeah,
Okay.
I think there's more question.
Is it now how many hermits can we have?
Okay, let me share my screen again. So the question is, how many hermits does this graph have now? Is that the question?
How many hermits can we, the maximum number of hermits can we have in the graph?
So in this graph, what happens is that we can, for each of these green edges, I can add a hermit. For each of these green edges, I can add a hermit. So I can have, I don't know, quite a few number of hermits, but it doesn't change my edge density. I just decided not to show these hermits because it doesn't make a difference. But for each of these green edges, I can add a hermit to this graph.
But it's interesting. Maybe how many hermits is it possible to add? Maybe it's some invariant.
Sure. Okay. Yeah. In general, yeah. That it is a good question. How many hermits can you actually add in terms of the number of edges or the total number of vertices? So I remember that for the lower bound of one planar graph, that's something that the authors did there. They looked at the number of hermits. So they did try to bound the number of hermits that can be present. Yeah, so that's something that they did for the lower bound on one planar graphs, but for two planar, I'm not sure. But that's something that we can look at.
So it is not known.
No, no.
And also, I want to ask: did you try to analyze such graph as a bipartite graph? And instead of crossings, we put vertices of, for example, different color, white, maybe such bipartite graph, some properties.
I'm sorry, I don't think I understand the question.
So you have graph, you have intersections.
Okay.
Instead of intersections, you add a vertex, which has another color, for example, white.
Okay.
And,
okay, so basically at each crossing, we add a vertex with a different color. Okay.
And maybe I'm just interested in some properties of such bipartite graphs, maybe. So did you try?
Sorry, stupid question here. Why would this be bipartite graphs?
Yeah.
Don't you have crossings that lie next to each other?
Yeah, so for two planar, it couldn't be bipartite.
Bicolored.
Oh, okay.
Bicolored, okay.
Yes. Mm-hmm.
Mm-hmm. Okay. So you would like to analyze or look at these bicolored graphs. Could be interesting though.
Or maybe,
but I'm not sure.
Yeah,
go ahead.
Yeah, just a similar like thought I had in mind. That like, wouldn't it, like, for example, help, I don't know, to study one planar graphs if like you take a two planar graphs and then instead of kind of extra crossings at like vertices, like just do, so that we obtain a one planar graph with more vertices, but just like kind of, I don't know.
If we at each crossing, if we just replace it with a vertex, then we basically
not each of them, but like
not each. Okay.
So that like some of them, I guess. So like if it's like there are two crossings, then like replace one and then
one of them.
I mean, this is likely not maximal one planar, right?
Yeah,
sure.
I see.
I guess. But
just in things like this, like kind of it feels like it would be nice if there were like kind of an induction step or something that would allow to reduce like more complicated stuff to easier stuff or whatever, but well, looks overwhelming. And another naive question then, like say in this construction on this slide, actually, like how did you understand that you have to choose like this graph on the right? Like
on the right, that was just basically try to find a small enough graph. So we know K9 is not two planar, and then we kind of try to go down. Okay, we remove one edge, two edge, and then at some point you reach a place where you're planar, two planar. So, yeah, I think the more interesting part was to obtain the graph on the left. which, yeah, that was also when we were trying to look at the low degree vertices for the lower bound. At some point, we thought that it should not be possible to have these, have 2 degree 6 vertices beside each other and be incident to a hermit. And initially I thought, okay, that should be true. And I thought that holds. And then we were trying to analyze the lower bound with that property. And then we figured out that it need not be true. They can actually be beside each other. And then at some point we obtained this grid, but in like a flat format. Yeah, and that's how we kind of realized that you can have this grid.
Okay, thanks. Yeah, I guess it's likely that there are
Thank
no
you
other
so
questions.
much.
Stop the recording.